Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to give you the final ingredient which will allow us to view the projective plane as a toric variety. And this final ingredient is the notion of a one-parameter subgroup. What this notion will allow us to do is to record the orbits of the torus acting on the projective plane using a lattice. So remember, the lattice is the way where we look at toric information combinatorially. Okay, so let's just remind ourselves of the basic setup here. So here we have the projective plane with homogeneous coordinates x0, x1, and x2. The complex torus T of dimension 2 is C cross to the 2. And we have the action on the projective plane as follows. Okay, so if you have Z1, Z2 inside the torus acting on this homogeneous coordinate, we've got a little bit of choice here, and the choice that we'll pick here is that the action here will map this point to x0, Z1, x1, Z2, x2. In other words, the Z1, Z2 scale the last two coordinates like that. Okay, so you can have a look at this torus action, and let me just remind you how this works. So here is the picture of its orbits. Okay, so the first thing is that if you pick a point like 1, 1, 1, the stabilizer of that point is going to be trivial. And so if you look at this 1, 1, 1, the corresponding orbit will be isomorphic to the torus itself. So if you pick that as a distinguished point, there is an embedding of this torus T inside the projective plane. Okay, so that's the first thing. So that's one orbit. So that's a two-dimensional orbit. We also have three zero-dimensional orbits corresponding to the coordinate points 1, 0, 0, 0, 1, 0, and 0, 0, 1. And then we also have three one-dimensional orbits corresponding to the three coordinate lines, and they're gotten by looking at each of the coordinate lines and removing the two coordinate points that it contains. Okay, so all up, three one-dimensional orbits, three zero-dimensional orbits, and one two-dimensional orbit. Okay, so the torus here, remember we're using Z1, Z2 as the coordinates here, so it is has coordinate ring C, Z1 plus or minus 1, Z2 plus or minus 1. And if you look at the embedding of this torus into here, that's going to relate to you, okay, the coordinates Z1, Z2 on the torus with the homogeneous coordinates on P2. And the relationship is, you can kind of just see it from here. Z1, okay, is going to be x1 on x0. Z2 is going to be x2 on x0. Okay, so that's the setup that we have where the torus acts on the projective plane. Let's introduce the notion of a one-parameter subgroup, which is quite useful generally in the theory of Lie groups. Okay, so here we'll look at a complex Lie group and look at the version for that. Let's suppose G is our complex Lie group. And then what is a one-parameter subgroup of that? Okay, so the first thing is that C cross, you can think of it as a one-dimensional group. Okay, and so a one-parameter subgroup is going to be just a Lie group homomorphism, complex Lie group homomorphism in this case, lambda from C cross to G. So I guess technically it's not a subgroup, but the image of this, unless this is trivial, and we include that case, so if this is not a trivial map, then this will be some sort of a one-dimensional subgroup that you'll get as the image of this lambda. Okay, so I guess the set of these you can write as the homomorphisms from C cross into G. We'll be looking at the complex Lie group, this T here, okay, which is C cross to the 2. And remember, the homs from C cross to C cross is Z, so the homs of C cross to T here is just Z2. Okay, so that's the notion of a one-parameter subgroup. And later we're going to relate this to a similar notion which we've already introduced, and that's the notion of a character of a Lie group. So in that case, you look at the homs from the Lie group into C cross. So you switch the order of these two. Okay, but more on that later. Okay, so let's have a little look at some examples of one-parameter subgroups. And I guess we know exactly how many there are inside T, okay, because this group is isomorphic to Z 2, so we just need a pair of integers. So let's pick a pair of integers like -1, and consider the corresponding one parameter subgroup. Okay, so that's the homomorphism lambda from C cross to T. And how does this work? So if you remember the natural isomorphism that you have here, what it's going to do is it's going to send some z, which is a non-zero complex scalar, to an element of this torus, okay? This two-dimensional torus is going to be z inverse, comma z inverse. Okay, great. So that's an example of a one parameter subgroup, and why are we interested in this sort of a thing? Okay. So this is the basic idea, okay? So what we kind of are doing when we study toric varieties is we have some torus that's inside this P2 and it's dense, okay? So since it sits inside P2 and it's dense, okay, it contains a lot of information about P2, but not all of it. How do you get the rest of P2? Well, you have to go to the boundary. And the way we're going to go to the boundary is by using one parameter subgroups as follows. Okay, so let's take this lambda of z. So this is inside our torus, and we let it act on this 1, colon 1, colon 1, 1. Okay, so it's going to move around inside this orbit. But to go to the boundary, what we're going to do is we're going to take the limit as z goes to 0. Remember, z equals 0 is not inside this C cross. But since you're inside P2, this lambda z dot 1, colon 1, colon 1, okay, so you're going to move around here, and as you move around, since this P2 is compact, okay, so it's in particular complete, it will always have some sort of a limit, and the question is, what is that limit? Okay, so let's do the calculation and work that out. Okay, so lambda of z, that's our value here, and we're going to let that act on this point 1, colon 1, colon 1. And the action is you just scale the last two coordinates. So it's 1 colon, you scale this one by z inverse, this one here, and this one by z inverse, so this one here. And so you have the limit as z goes to 0 of this. Okay. Now, as I said, this is projective, so and in particular compact. So it does have a limit. How do we work out the limit? Well, I guess this point here, you can just multiply throughout by z, because inside this orbit, that's going to be defined, okay? So if you multiply by z, you get z colon 1, colon 1, and you take the limit as z goes to 0, and now it's very easy to see what that limit is. It's just 0, colon 1, colon 1. Okay, so that's rather nice, because this here is not inside T, the copy of the torus inside P2. The copy of the torus inside here, you're just scaling these last two coordinates by non-zero scalars. So it's just where these three coordinates are all non-zero. Here, this first coordinate, or the coordinate corresponding to index 0 is 0. So this is not in there. In fact, if you have a little think about it, you look at this coordinate line. It contains 0, colon 1, colon 0, and 0, colon 0, colon 1. Okay, so that's the coordinate line where x0 equals 0. Okay, and this is on there, and this is going to be this point there. Okay, so 0, colon 1, colon 1, that's going to be a point on this one-dimensional orbit. Okay, and if you let the torus act, it will give you that one-dimensional orbit. So as z goes to 0, you start here, okay, with z equals 1, and then as you move, it'll go to here like that. I guess another thing that you can do if you want to get another point on the boundary is you can let z go to infinity. Let's do the same thing. Let's z go to infinity and see where this point heads off to. So you put z equals infinity here, and I hope you can see clearly that, of course, this goes to 1, colon 0, colon 0, which is the 0-dimensional orbit up here on the other side. So you go to here. So that's one way that you can access points on the boundary. You just take limits. And the question is, what do you take limits of? How do you go there? And so the way we're going to do it is we're going to pick these one parameter subgroups. We know there are lots of them. And so hopefully we can get everywhere. And so what I want to do is I want to examine all these limits. So we try to approach the boundary, okay, of this torus. Okay, so that's how we're going to get at all those missing points of the projective plane by looking at these limits of these one parameter subgroups. Okay, so this proposition is going to tell us exactly what happens, and we're going to see how we can encode this orbit decomposition in a lattice theoretic way. Okay, so we're going to produce a lattice which is going to tell us all that information. So what is the lattice? The lattice is the Z2 here, and that's going to give us all our one parameter subgroups. So for each pair of n1, n2, these are just the integers here, we're going to have a one parameter subgroup. So that's a homomorphism C cross to T. And what is that homomorphism? It sends this non-zero scalar Z inside C cross to the pair Z to the n1, Z to the n2. And what we're going to do is we're going to just look at the limit of this one parameter subgroup as you hit this point 1 colon 1 colon 1, or as you look at its image by this map, okay, the natural embedding, our chosen embedding. Once you pick this distinguished point, that's our chosen embedding of the torus inside P2. Okay, and we're going to look at the limit as Z goes to 0. And that's going to be a different point depending on what n1 and n2 are. Okay, so what I'm going to do is I'm going to tell you what all these limits are, and it will depend on what n1 and n2 are. So here, what I've drawn, okay, there's quite a lot of information here, is basically the n1, n2 plane. Okay, and for each of those points, I'm telling you what is that limit. Okay, and so let's have a little look at the example that we've already got here. If n1, n2 are minus 1, minus 1. So let's look on this picture where that is. So you have n1 equals minus 1, n2 equals minus 1. So you're down on this line here, this diagonal line. Okay, and then this picture says that the limit is, it's given by here, 0 colon 1 colon 1. That's what we computed, 0 colon 1 colon 1. And that's true for any n1, n2 on this part. So that's true for not just minus 1, but minus 2, minus 2, minus 3, and so forth. If instead of z inverse here, you had z to the minus 2, z to the minus 2, of course, similar calculation, except for now you get a z squared here, you'll also get 0 colon 1 colon 1. So everything along here, if you pick any of those one parameter subgroups and take the limit as z goes to 0, you always get 0 colon 1 colon 1. Let's look at the other example where you have z going to infinity of this was 1 colon 0 colon 0, 0. Of course, another way to do that is to, instead of picking minus 1, you look at z goes to 0 of plus 1, comma plus 1. And that will give you this point. So if you look at plus 1, colon plus 1, okay, and you look inside here, what does this diagram say? It says that the limit point should be 1 colon 0 colon 0. And that's the thing that we computed here. Okay, so that's really, really nice. Okay, so so this is just a calculation, okay, to see what this is. But let me sum up briefly what's happening in this diagram. Okay, so what are the possible limit points that you can have? In fact, the only possible limit points are the ones which have either a 1 or a 0 as the coordinates. Okay, so there are 7 of them because you can't have 3 zeros. Okay, so there are 7 possibilities. Okay, and you can kind of see from this calculation that's the type of thing that you expect. Okay, and in fact you do get all 7 possibilities, okay, inside this diagram. So firstly, the point 1 colon 1 colon 1, that will only occur if n1 and n2 are 0. If n1 and n2 are 0, okay, so that's going to be the trivial case. Z maps to 1, n1, n2 are 0, so that's 1, 1. Okay, 1, 1 doesn't scale anything, so you just stay put here. Okay, so that's the limit that you have here. Okay, so what other points can you get at? You can get at all the 3 zero-dimensional orbits as well. 1 colon 0, 0, 0 colon 1, 0, and 0 colon 0 colon 1. Okay, so how can you get them? Well, if n1 and n2 are both positive, you'll get 1 colon 0, 0. If n1 and n2 are in this region here, this 2-dimensional region here, you get 0 colon 1 colon 0. And if n1 and n2 are in this 2-dimensional region here, you get 0 colon 0 colon 1. And finally, you can get the 1-dimensional orbits. There are 3 1-dimensional orbits if you're on these rays. Okay, so not including this point here, the open rays. Okay, as you go out here, this will give you 1 colon 0. On this open ray here, you'll get 1 colon 0 colon 1. And on this ray here, you'll get 0, colon 1, colon 1. And that's something that we've seen already. Okay, so this is the picture that really tells us, lattice theoretically, how we record the orbit data. So instead of drawing this, okay, what we'll see is that if you have a torus, as soon as you have a torus, you're going to be able to picture the orbits by sort of breaking up this lattice, okay, into various regions. And it's rather interesting what happens here. So the two-dimensional orbit, okay, that you get here will correspond to like a zero-dimensional bit here. It's just the point, this one lattice point. The three zero-dimensional orbits will correspond to these two-dimensional regions, and the one-dimensional orbits will correspond to these one-dimensional rays, as it turns out. Okay, let me just show you how to prove this, and it's really just the same type of calculation that we've performed here, but let's just do a simple case. Suppose, for example, you want to look at all the cases where the limit point is 1, colon 0, colon 0. So what is the action of this lambda n1, n2 on that 1, 1, 1? So if you let this act on 1, 1, 1, you just scale the last two coordinates by zn1 and z to the n2 here. So you have 1, colon z to the n1, colon z to the n2. And if you want this to equal 1, colon 0, colon 0, of course, these are the same as in terms of homogeneous coordinates, but since there's a 1 here and a 1 here, you can't scale. So that means that for this to equal 0 and 0, you want these n1 and n2 to be positive. And that's why you have this region here like that. Okay, so this is the picture that really nicely is if you want to study toric varieties, okay, and you want to say, okay, let's record the information of P2. This is the picture that one gives, okay. This is exactly what you have. So I'm going to introduce a little bit more notation here. So this region here, this two-dimensional region, I'm going to call sigma 0, and it's going to be the closed one. So it's going to include this boundary ray here, this boundary ray here, and also this boundary vertex here. So that's going to be basically this subset of the lattice, okay, Z2, it's n times 1, 0 plus n times 0, 1. This positive quadrant. Similarly, sigma 1 will be this region here. Okay, so it's going to be n times 0, 1 plus n times, so that's 0, 1 here, and then it's also spanned by this point here, minus 1, minus 1, and similarly sigma 2 is going to be n times 1, 0, that's out here, plus n times minus 1, minus 1, so that's going to give us this region here. Okay, so now that's great. We have a way of encoding in a lattice, okay, all the orbits. And the other thing is that we saw that this orbits, okay, that's one way that we can look at this projective plane and also get at the affine patches, okay. And I want to show you how that works. So this is the really, really nice thing that comes into play. And what's key here is the duality between one parameter subgroups and characters of T. Okay, so before I go into the actual duality, which is what I'll explain here, I want to introduce certain what's called the dual of these cones. So these regions here, sigma 0, sigma 1, sigma 2, they're going to be cones, two-dimensional cones, okay, because they're spanned by essentially two vectors like that. And what are the duals? What's sigma I check? So all this lives inside Z2, and then we're going to have a dual copy of the Z2, which of course is just Z2. And what we're going to do is we're going to look at all those vectors in Z2 such that, and this is my notation of the dot product of this M with anything inside sigma I, so any n inside sigma I is going to be non-negative. That's going to be the dual cone. Okay, so let's have a little look at that and work out what that is. Okay, so here sigma 0, this is this bit here. So if you want to make sure that you pick a vector now, okay, integer vector now, such that the dot product with anything inside here is positive, of course that's just also just a positive quadrant, okay, this here, including the axes. And one easy way to see this is that, well, for example, if you want to be able to dot with anything here and be non-negative, you have to be able to dot with the standard basis vector, this one here, 1, 0, and be positive. So you have to be on this part of the half plane. And you have to, when you dot with this one here, you'll also be positive. So you have to be above this. So you'll certainly be in this region. But anything else is going to be a non-negative linear combination of those two. So if you're going to have a non-negative dot product with those two, you're going to have a non-negative dot product with everything else inside here as well. In other words, to have a non-negative dot product with anything inside here, you just have to have a non-negative dot product with 1, 0 and 0, 1. Okay, so that gives you this region here. Okay, let's just go through the other two regions here. So inside here, if you want to have a non-negative dot product with everything inside here, you have to have a non-negative dot product with 0, 1. So that's this one here. Okay, 0, 1 is pointing up. So you have to be above this N1 axis. And then you have a non-zero dot product with -1, -1. That's pointing down this way. So the perpendicular line is like this. So you have to be below this perpendicular line. And you get this region here. And finally, let's do the same thing for this sigma 2. Okay, so you want to have a non-negative dot product with this 1, 0. So you're on the right half plane. And then you want to have also a non-negative dot product with this -1, -1, which we saw was just below here. So you're in this region here. And I hope this looks familiar. Okay, if you look back at the first video in my little introduction to the projective plane as a toric variety, you'll realize that this is basically the information which gives you the 3 affine patches, okay, for your projective plane. So remember, the projective patches are what give the projective plane its manifold structure. So here this corresponds to this U sigma 0 check corresponds to U0, the affine plane with coordinates x1 on x0, x2 on x0. This bit here, okay, corresponds to affine plane where essentially x1 is non-zero, and this here is the affine plane where x2 is non-zero. Okay, so is this a miracle or what's really going on? So let's find out what's really going on. And the key here is the duality between one parameter subgroups and characters of T. So this is the key thing here. So what is this duality? So what's going on? So let's take this one parameter subgroup, okay, lambda, n1, n2, and I'll write this n1, n2 now as just a vector like this, n vector. And that's going to be a Lie group homomorphism from C cross to T. Okay, so what's going on here? So inside this picture here, remember, these are basically characters of the torus. Okay, so each of the lattice points here correspond to characters of the torus. Okay, so they're given by this chi m vector. Okay, and a character of the torus, okay, so remember the characters of the torus means it's a function on the torus. Okay, these are the functions on the torus. Okay, so so there's a Lie group homomorphism, complex Lie group homomorphism from T to C cross. And so you can compose the two as well, and that will give you a complex Lie group homomorphism from C cross to C cross, which is basically has to be of the form just raising Z to some power. And what is that power? Okay, so let's have a look at this. So this is basically the duality. Here you have a one parameter subgroup, you compose it with a character, and then you get something that's fairly simple. That's just a complex Lie group homomorphism C cross to C cross. Okay, so it's Z to some integer power, essentially given by some integer. Okay, so basically you pair them. And what's the pairing? Well, let's take this lambda n vector here, and let's apply chi of this m vector. Okay, so if m1, m2 give you the m vector, then what you do is you take the m1th power of this and you multiply the m2th power of this. Okay, so you'll get n1, m1 as the power of z coming from here, multiplied by n2, m2 as the power of z coming from here. And of course that means that you're just taking the dot product of n and m. Okay, that's the power of z that you have here. Okay, so this is how the dot product comes in. Okay, so really this composition of the one parameter subgroup and the character really just is the dot product. Okay, so that's the key point. That's the duality that you have between these two notions. Okay, so let's use this duality now to explain why you actually get these affine patches, and that depends on the way I kind of defined what these affine patches were. Okay, so how did I define what the affine patches were? So basically I said that, well, what do we do? What we're going to do is these affine patches, okay, the way I introduce this projective plane as a toric variety is to say that, well, what we'll do is we'll look at these zero-dimensional orbits. Okay, and now we know how to access them using this picture here. They correspond to the two-dimensional regions. Okay, we're going to look at them, and then we're going to say it's going to be all those functions on the torus. Okay, so they just have to be defined on that open dense subset of P2 that happen to be defined at those particular points as well. Okay, so that's what we wanted. Okay, so what we'll do is, so in other words, this character chi m is inside this patch ui. Okay, defining that ui just means that what you do is the first thing is you look at those points which give you these orbits. So remember, for example, if you're defined, let's pick example, here's x. 0 is non-zero, okay? If you're defined here, you have to be defined not just here, but also on every orbit whose closure contains that point, okay? So if you're defined here, you're defined on a neighborhood of that point, so you're also defined on this orbit as well, and of course the open orbit, okay? So you look at those three orbits, okay? So what are those three orbits? So you've got 1, 0, 0, it's 1, 0, 0 here, and you've got the one that's the orbit of 1, 0, 1, 1, 0, and also the orbit of 0, so this one, 1, 0, 1, 1, 0, 1. So that's basically all of sigma 0, okay? So you have to add that one too, right? So the sigma 0 is the closure of that bit. So it's the whole positive quadrant, including these n1 and n2 positive axes, okay? So what you'll do is you look at all those points, and they're basically given by the limits of all these lambda n of z's as n ranges over sigma I. And then you want to make sure that chi of m, when you apply it to this, so remember chi of m is continuous, so you can slip the chi m through the limit sign, okay? You want those to be defined. But what is this value here, okay? So this value here, so I guess here I should have written, let me just fix that up. So this value here is just the limit as z goes to 0. We've computed what this is by the duality. This is just z to the n dot product m. And you want the fact that when z goes to 0, this is defined. So this is just some power of z, and it's always going to be defined as long as this power is not negative, right? Because you're going towards 0. As long as you're not going towards 0. So this means that you want this to be non-negative. So the dot product is non-negative. And that's where this condition comes from here. So that's why we see that this sigma I check is a way where we recover this old definition of the affine standard patches, okay? So this is a really, really beautiful picture. I hope you can appreciate it. If not, do go back and have a look over this video. But let me just sum up what the main things are of this video here. So what we've managed to show is that when we look at this projective plane, okay, we're going to study this torically. And one of the things now is that we have a way of encoding the orbit decomposition, okay? And this is the way an algebraic geometer, a toric geometer would do that, and that's using the lattice of, in this case, it's the lattice of one parameter subgroups of the associated torus. And what we do is we just break it up into regions, okay? So the limits of these one parameter subgroups as z goes to 0 will give you various points. If it's not going to be 0 here, it's going to give you various points actually on the boundary, and you'll get all the orbits that way, okay? So we just break this up, and it's kind of nice, the picture that you see here, how it breaks up. And there's actually a lot of things going on. For example, you can really see a lot about what's going on here. For example, there's sigma 0 and the sigma 1, okay? They will correspond to 1, 0, 0 and 0, 1, 0. 1, 0, 0 and 0, 1, 0. Okay. But in between the two regions here, you'll have this 1, 1, 0. 1, 1, 0. And that's actually just the orbit that goes, the one-dimensional orbit that goes from this zero-dimensional point to this zero-dimensional orbit, rather. Okay, so it connects those zero-dimensional orbits. So that information is in there as well. And similarly, when you go from here to here, you get a similar thing happening. So that's, of course, symmetric. So that's why you get a triangle. It's dual picture. So this presents all the information about the orbits. And then once you have this information about the orbits, it also is going to tell you a lot of information about the actual variety, okay, as a manifold, okay, so as a variety. And the way you do this is you take this and use the duality between the one parameter subgroups and the characters of T. So in terms of this lattice, okay, when you change from multiplicative to additive notation, this means that you look at what are called these dual cones, and you look at the dot product, okay, and you get these dual cones. And these dual cones will give you these affine patches. And furthermore, if you analyze a bit further, and I'll show you how this works in general when we study the toric varieties more generally, you can see how these affine patches really patch together. I hope you enjoyed this adventure in pure mathematics.